Can we grow food on the moon or Mars? The journey to sustain life beyond Earth isn't just about launching rockets and exploring the cosmos. It's also about solving a very human problem: food. Supplying astronauts with food is not just a logistical challenge, but an expensive one. A single astronaut on the International Space Station requires approximately 1.8 kilograms of food and packaging per day. Imagine multiplying that need over a multi-year mission to Mars, where weight and space are at a premium. This is where the concept of space farming emerges, not just as a necessity, but as a potential breakthrough. Growing food in space offers the promise of a self-sufficient ecosystem, turning waste into resources. Just 10 square meters of crops can provide essential oxygen and nutrients for a sustainable habitat. But the challenges are formidable. Reduced gravity, radiation exposure, and limited resources on celestial bodies like Mars require innovative solutions. For instance, while Martian soil is rich in minerals, it's deficient in reactive nitrogen, crucial for plant growth. Scientists are exploring nitrogen-fixing bacteria and other strategies to overcome this hurdle. Pioneering experiments from the Veggie system on the International Space Station to the Eden ISS project in Antarctica are paving the way. Yet, as we delve deeper into these innovations, one must ask, could these advancements be the key to unlocking human colonization of space? Long before space agriculture became a reality, visionary minds were already dreaming of it. In 1933, Konstantin Tsiolkovsky, a pioneering Russian scientist, envisioned growing plants in orbital stations. At a time when space travel itself was still a distant concept, Tsiolkovsky was already pondering how humans might sustain themselves on journeys beyond Earth. His ideas laid the groundwork for what we now term space farming, a discipline crucial to the prospect of long-term human habitation in space. Space farming involves cultivating crops beyond our home planet, whether aboard space stations or on celestial bodies like the Moon or Mars. The environments differ, as farming on celestial bodies may bypass the complexities of microgravity, but each presents unique challenges. These include limited inputs like soil media and insulation, as well as the availability of vital gases such as carbon dioxide, nitrogen, and oxygen. Tsiolkovsky's early vision of an artificial ecosystem has evolved into a practical necessity, as the cost and impracticality of resupplying emissions drive us towards self-sustaining environments. But even as we continue developing these technologies, another question beckons. How do we contend with the myriad technical challenges that await on other worlds? Space farms offer more than just a solution to humanity's quest for off-Earth sustenance. They form a closed-loop ecosystem, crucially recycling air and water, reducing waste, and providing much-needed fresh food for astronauts. Picture this. A compact area of just 10 square meters of crops can produce 25% of the daily requirements of one person. It's a natural cycle where plants purify the air, recycle wastewater, and even convert waste materials into nutrients, transforming space habitats into self-sustaining ecosystems. The fresh food grown also serves to bridge the vitamin gap long space missions impose, as well as improve the taste and texture of astronauts' diets. Yet, the path to cultivating these space farms is not without hurdles. Farming in space or on celestial bodies like Mars confronts unique challenges. Microgravity, radiation exposure, and low-pressure environments alter plant growth and require innovative solutions. For instance, while Martian soil contains many essential minerals, it lacks reactive nitrogen, a void that nitrogen-fixing bacteria might fill. As we harness technologies from projects like the Veggie system on the ISS or the Green Hab in the Utah desert, we inch closer to perfecting space agriculture. But the question remains, can our ingenuity overcome these cosmic challenges to truly settle the heavens? Undoubtedly, space farming faces monumental challenges, particularly with the trifecta of microgravity, radiation, and low-pressure environments. On a space station or space colony, microgravity alters plant growth, affecting their size and growth rate despite the provision of directional light. This unique environment hampers the development of root and shoot systems, often resulting in smaller plants. Meanwhile, celestial bodies like Mars, with only a third of Earth's gravity, present their own set of hurdles. Here, plants must contend with intense radiation levels that can damage DNA, impairing germination and growth. This radiation can disrupt photosynthesis, leading to potential losses in function essential for plant survival. Additionally, the low-pressure conditions on Mars can impact photosynthesis and evapotranspiration rates. Yet, studies show that elevated CO2 levels could offset these hypobaric challenges, indicating a possible path forward. Martian soil, though rich in minerals, lacks reactive nitrogen, crucial for plant growth, hinting at the necessity for nitrogen-fixing solutions. While experiments have shown plant survival in simulant Martian and lunar soils, reaching full maturity remains elusive. As these technical barriers persist, the question arises, how can these insights transform our approach to extraterrestrial agriculture? In the next chapter, we delve into pioneering experiments that might just unlock the secrets to thriving space farms. Martian soil presents a unique challenge for space farming, as it lacks reactive nitrogen, crucial for plant growth. Without this, plants struggle to thrive. However, a potential solution lies in the use of certain nitrogen-fixing bacteria. These microorganisms, when introduced into Martian soil, might convert atmospheric nitrogen into a form that plants can use, thus enriching the barren soil. Research has shown that plants can germinate and survive on simulant Martian soils for limited periods. Yet, achieving full growth, like flowering, remains a hurdle. Only 1 out of 4 species tested managed to reach this stage, highlighting the need for further exploration of soil amendment strategies. Intriguingly, despite these challenges, Martian soil contains most minerals necessary for plant growth. This suggests that with the right biological aid, such as bacteria, we might unlock the potential for sustainable agriculture on Mars. The promise of these microorganisms could transform Martian landscapes into fertile grounds for crops. Next, we turn to groundbreaking experiments that not only test these theories, but also push the boundaries of what's possible in extraterrestrial agriculture. How might the lessons learned from these trials pave the way for the first seeds to sprout on another planet? Let's explore the pioneering work under the harshest conditions and see how close we are to making space farming a reality. Building on the foundation of Konstantin Tsiolkovsky's early visions, today's experiments on the International Space Station and beyond are transforming the dream of space farming into reality. The NASA Vegetable Production System, affectionately known as VEGI, is a pioneering initiative aboard the ISS. VEGI's deployable unit focuses on growing salad-type crops, providing fresh produce to astronauts and a critical boost to their nutritional intake. Meanwhile, back on Earth, the Mars Desert Research Station in Utah continues to simulate the Martian environment inside its GreenHab, a greenhouse designed to confront the unique challenges of growing food on Mars. Remarkably, the 2019 Chang'e 4 lunar mission took a giant leap forward by carrying the lunar micro-ecosystem. This 3-kilogram biosphere aims to test whether plants and insects could coexist and thrive on the moon's surface. As these experiments unfold, the Alina lunar lander is set to further explore plant growth in space with its upcoming lunar plant growth experiment. Each of these efforts, from 3D food printing to the Eden ISS project in Antarctica, marks a critical step in understanding how we might sustain life far from Earth. As we delve deeper into these pioneering experiments, one question remains: can we overcome the hurdles of radiation and reduced gravity to make thriving space farms a reality? The answer may lie in the stars. Looking ahead, the future of space agriculture is poised on the brink of groundbreaking missions and projects that could redefine our relationship with the cosmos. Teams from around the globe, including NASA, are actively refining techniques to ensure not just survival, but a thriving agricultural presence on celestial bodies like the Moon and Mars. These efforts aim to overcome the distinct challenges of each environment, such as varying gravitational forces and the absence of critical nutrients in Martian soil. Innovative solutions, like nitrogen-fixing bacteria, are being explored to address these hurdles. Projects like the Eden ISS in Antarctica offer a glimpse into the possibilities, simulating conditions that might be encountered on Mars. This initiative, along with experiments on the International Space Station, is laying the groundwork for self-sustaining ecosystems beyond Earth. The path forward involves cultivating a variety of crops, from potatoes to peppers, each chosen for their potential adaptability and nutritional benefits. As these endeavors progress, they not only promise to sustain human life in space, but also compel us to rethink agriculture here on Earth. Could the lessons we learn from space farming shape a more sustainable future for all of us?